This section's title simply introduces the topic. We'll be analyzing the results from a validation curve generated for a support vector machine, SVM. A validation curve shows how a model's performance changes with different hyperparameter settings, in this case the regularization parameter, C. This is where the quiz question starts. We're given a scenario. A validation curve displays the performance of an SVM classifier as the parameter C varies. The goal is to determine which statements correctly interpret the relationship between training and validation scores shown in that curve. Here, the context is set. We are using a tool called ValidationCurveDisplay from a Python library, SCIKITLEARN, to visualize an SVM's performance. The key is the behavior described. Training score goes up steadily with increasing C, but the validation score increases, peaks, and then drops. This setup is essential for understanding the following quiz options. This part explains how to approach the problem. The method relies on interpreting the validation curve. No complex calculations are needed. Just understanding the relationship between training and validation performance and how it signifies underfitting or overfitting. This section reinforces the previous one. It emphasizes that the problem is solved by careful observation of how the training and validation scores behave against the C parameter, with the goal being proper model selection to avoid overfitting or underfitting. This introduces a structured approach to answering the question. This helps in systematically analyzing the given data to arrive at the correct answers. The first step is analyzing the training curve's behavior. The higher the C parameter, the better the model fits the training data. This is a good sign for fitting the training data but doesn't necessarily mean the model is good at generalizing to new data. Okay, Vamsi, let's break this down. The problem is all about understanding a graph, a validation curve, showing how well a support vector machine, SVM, model performs with different settings of a parameter called C. This parameter controls how much the model is allowed to adjust to fit the training data. Too much adjustment leads to overfitting, and too little leads to underfitting. The goal is to find the best C value based on the validation curve's information, which shows the model's performance on data it has not seen before, and not just on the data it's trained on. Here, we are observing two things. First, as we increase C, the training score improves. This means that the model is doing a better job of correctly predicting the data it has already seen. However, this doesn't always translate to better performance on new, unseen data. That's where the second observation comes in, where the validation score is also observed. Second, the validation score is observed. Now, the fun part. A multiple-choice quiz to test your understanding of the validation curve's meaning. Remember, the goal is to choose which statements are true based on how the training and validation scores behave. Hey Vamsi, this question presents a scenario where we're using scikit-learn's validation curve display to see how well a support vector machine, SVM, works with different levels of regularization, controlled by the C parameter. We're plotting how well the model performs on the training data and a separate validation dataset against different C values. Think of C as a knob that controls how much the SVM cares about fitting the training data perfectly. Too much and it'll overfit, too little and it'll underfit. This statement explores the possibility of overfitting when the C parameter is high. Let's investigate. Overfitting happens when the model learns the training data too well, performing great on it but poorly on unseen data. A high C value makes the SVM very sensitive to the training data, potentially leading to this problem. Let's think critically. Is it always true or are there conditions where this might not happen? This statement suggests that a smaller C value is better based on the validation score. The validation score shows how well the model generalizes to unseen data. If a lower C gives a better validation score, it likely means the model is avoiding overfitting while still achieving a good performance on new data. Consider this. Would a low C always be best, or are there scenarios where it would be suboptimal? Here, we consider the possibility of underfitting with low C values. Underfitting occurs when the model is too simple to capture the underlying patterns in the data. A low C value restricts the SVM's ability to learn complex relationships, This is important to note. Let's examine whether underfitting is always a certainty at low C values or if the context of the validation score might alter this conclusion. This explores whether maximizing the training score is the key to finding the best C. However, we're primarily interested in how well the model performs on new, unseen data, which is what the validation score measures. Focusing solely on the training score can lead to overfitting. Think about this. Why is validation performance more crucial than training performance for model selection? Okay, let's break down this SVM model performance analysis. We're looking at how well a support vector machine, or SVM, is doing. SVMs are powerful classification models, but their performance hinges on a key parameter. C, the regularization parameter. This analysis uses a ValidationCurveDisplay to visualize how the model's accuracy changes as we tweak C. The ValidationCurveDisplay plots two important scores against different values of C: the training score and the validation score. The training score reflects how well the model learns the data it's already seen. The validation score shows how well the model generalizes to new, unseen data. This is what truly matters. This is the core question. We're examining the relationship between the C parameter, the training score, and the validation score. The goal is to identify which statements accurately interpret the results displayed by the validation curve. Let's consider option A. High values of C mean the SVM model is allowed to be very flexible and complex. If the training score is high but the validation score is low at high C values, that's a classic sign of overfitting. The model learns the training data too well and doesn't generalize to new data very well. So, we need to see if the validation curve indeed shows this behavior. Option B suggests that a lower value of C is better. This is possible. A lower C implies a simpler model, less prone to overfitting. But a very low C could lead to underfitting. Therefore, we need to determine if the peak validation score occurs at a relatively lower C value, suggesting that's the best C to use. Option C proposes that the model is underfitting at low values of C. Underfitting means the model is too simple to capture the underlying patterns in the data. If this is true, both training and validation scores would be low at low C values. The validation curve should show us if this is happening at the lower end of the C parameter values. Option D claims that the optimal C value is the one that maximizes the training score. This is generally incorrect. While a high training score is desirable, we're ultimately interested in how well the model generalizes to unseen data, which is reflected in the validation score. So the optimal C is the one that produces the best validation score, not the training score. Looking at the validation curve, we see that the model's performance on new, unseen data improves up to a certain point as the regularization parameter C increases. Beyond that optimal point, performance drops off as the model starts to overfit the training data. Therefore, a lower value of C, which is in the range where the validation score is highest before the drop-off, would be preferable. We select the parameter which yields the best performance based on the validation score, not the training score. As parameter C increases, the training score keeps climbing, showing the model is learning the training data really well. However, the validation score peaks and then decreases. The widening gap between the training and validation scores at high C values is a telltale sign of overfitting. The model is becoming too specialized to the training data and not generalizing well to new data. At very low values of C, the model is too simple and constrained. It's not capturing the complexity of the data, resulting in poor performance on both the training and validation sets. This is known as underfitting. It's worth noting that the validation curve will still increase before eventually peaking and then decreasing in the presence of underfitting. While the training score might look good if you picked a high C value, that value does not reflect performance on new data. The optimal value of C should maximize the validation score, not the training score. The goal is to build a model that generalizes well to unseen data.